The topic of our today's discussion is the PCM frame primarily. I am referring to chapter number 8 of our textbook, which is Telecommunication Systems Engineering by Roger L. Freeman. So, what we have already discussed in our earlier PCM discussion was that PCM is a format of converting an analog signal to a digital signal, and uh, and combining or multiplexing a large number of digital signals into one particular frame. And we have already discussed that there are two types of signals, uh, basically two types of PCM formats that are used all over the world. Number one is the European standard, which takes us to the E1 format, and the other standard is the American standard, which takes us to the T1 or the DS1 standard. Uh, I'll be following this chapter article by article. So it is this presentation is quite different from the one that I have already sent, which is named PCM only. This is the name of this presentation is PCM frame. This is the name that I've given it because we'll be talking about the frame of PCM quite a lot. This is the most important diagram of this chapter. I would recommend you to see in detail. Uh, First of all, the PCM multiplexing is carried out in the sampling process. So two things are happening at one particular time. Number one is that the multiplexing of multiple channels is being done, and the other thing is that these channels or these signals are being sampled. If we see this, for example, here we have the first channel coming in, here we have the second channel coming in, and here we have the third channel coming in. All these channels come through this sampler. This is a sampler. This is a sampler, right? What happens is that each signal gets its fair share in time and is sampled for that particular time. Here we are showing three different samples, and we've got three contacts in this particular switch. So this switch is getting the information from this. This switch is getting the information from this channel at first, and when it moves to the second one, it gets the information from this channel, and after that it gets the information from this channel. But this is done quite synchronously, and all the signals are sampled in one particular pulse amplitude modulated signal. Now this information goes into the quantizer, and what does the quantizer do? Quantizer and the encoder, it gives first of all, it gives particular integer values to each and every signal that we are getting, and the encoder, what encoder gives is that it encodes it that particular value into binary, and this And in this way we get a digital signal in this uh, format, and it is sent over a certain distance, and it is received, and then we have got a decoder over here, and from that decoder we get the same PAM signal that we created earlier, and that is recovered, and from that uh, point we enter into a sampler. And what does a sampler do? It gives the same values to the three different channels, and so the three different channels are available at three different ports here, in this case 1, 2 and 3. This is the whole story. I would recommend you to create a digital circuit. You can use Proteus or whatever simulation platform to simulate this action, and afterwards this section, so that uh, we are able to uh, create a PCM modulation and demodulation on both the sides, so that we have got three different signals coming in, which are analog, and they are digitized, and afterwards they are encoded and then sent, then received, decoded, um, and then again sampled, and the original analog signals are recovered. After sampling, quantization and coding, we have a bit stream of ones and zeros as given here. Identification of the beginning of scanning is uh, uh, that is required. That is basically required. So we need to have some framing bit which identifies that now this particular signal is being sampled. And how do we do that? And why do we do that? We do it so that the far end receiver should know exactly when the sampling sequence starts. The receiver knows in advance that a 28-bit slot will follow. It synchronizes the receiver. Such identification is done by a framing bit. Let me tell you, this framing bit is in addition to the 24 time slots that we are talking about, that we have been talking about earlier. One full sequence of samples is called a frame. 24. No, let me remind you that we are talking about North American DS1 system, not the E1 system which is used in Europe. In North American DS1 system, 24 channel PCM system with 8-bit coding, that is 2 raised to power 8 equal to 256 quantization steps, or distinct PCM code words are used. Supervisory channel is in band. How is it done? The bit 8 of every sixth frame is robbed for supervisory channel. So we have got uh, 24 time slots in a DS1 system, and after every sixth frame, the bit number 8 is taken and it is used for the supervisory signal. One bit is added as a framing bit, or it is also called the S bit. Now this S bit is in addition to the 24 time slots. DS1 consists of 8 into 24, 8 bits and 24 time slots. We get 192. And we have got this one S bit, which is the framing bit, in addition to those 192, and we get a total frame of 193 bits. Now, as we know that 8000 frames are transmitted per second because of the Nyquist criteria, Nyquist sampling rate. So 4000 into 2 gives us the value 8000. So the bit rate of DS1 or T1 is 193 into 8000, which gives us 1.544. So that's how we come up to this particular data rate. Now let's see an actual DS1 signal. How does it look like? We are looking at one single frame, and one single frame takes 125 microseconds to pass through. It means that it has got 125 microseconds to pass through. Here you can see the S bit comes in the first place. It tells that the new frame is coming. After that, the first, second, third, fourth up to eighth, 8. Then the second octet is here. Then third, then fourth. So a second, and then the third. Now we have got this is 8 uh, 8 time slots. Then this 8 time slots, and or this is the first time slot, this is the second time slot, and this is the 24th time slot. Basically these are the 24 time slots, and this is the S is the first bit. If we multiply 24 with 8, these are all 8 bits in this time slot. In this time slot we've got 8 bits, 8 bits, 8 bits, and also in between from every time slot has 8 bits. So in this way we have bit rate. How many bits are available in this frame? 193, right? Now in the European E1 system, what happens is that it consists of 32 channels, of which 32 are used for speech or data, if they are used for it, and are derived from incoming telephone trunks. Basically, these are the 30 voice channels which have been digitized and converted from the analog format to the digital format. The remaining 2 channels transmit the synchronizing, alignment, and signaling information. Here the system is a little bit different from the North American system, because in North American system we have an S bit or the framing bit. This is not the case in the E1 or the European system. Each channel is allocated an 8-bit time slot, and they are tabulated as shown below. We start from 0 and go to 31. The 0th time slot is used for synchronizing or framing. From 1 to 15 it is used for speech. Then the 16th one is used for signaling, and 17 to 13 it is used for speech again. So we have got 30 channels for speech, 1 channel for synchronizing and framing, and 1 channel for signaling, and that is the 16th. In time slot 0, a synchronizing word or code or word is transmitted every second frame, occupying the digits through 2 to 8 as 0011 You can see these are the bits 2 to 8. The second bit is 2, third is second bit is 0, third is 0, fourth is 1, fifth is 1, sixth is 0, seventh is 1, and eighth is 1, as shown here. Let me show you here. In frames without synchronizing word, the second bit of time slot 0 is frozen to 1, so that these frames in these frames the synchronizing word cannot be imitated. So in this way it is identified that uh, that a new frame is coming. Uh, that is that it is the start of a new frame. Remaining bits of time slot 0 can be used for the transmission of supervisory information. Now even data rate. E1 transmits 32 channels of 8-bit time slots. An E1 frame therefore has 8 into 32 is equal to 256 bits. There is no framing bit, and the framing alignment is carried out in TS0 as explained in the previous slide. So the E1 bit rate to the line can be calculated as 256 multiplied by 8000, and we get 2048000 or 2.048 Mbps. This is the data rate of an E1. Now, how is what is the difference between framing and timing? Framing ensures that PCM receiver is aligned regarding the beginning and end of a bit sequence or frame, so that we should know that a new frame is starting. While timing refers to the synchronization of the receiver clock that is it is in step with the companion far end transmit clock. It means that uh, uh, the the receiver clock and the transmitter clock should be synchronized. That is called timing basically. And timing at the receiver is corrected via the incoming 1 to 0 and 0 to 1 transitions. So we need to check that periods of no transitions do not occur, or should be less in number. Now let's see what is quantization distortion. It is the difference between the signal waveform as presented to the PCM codec and equivalent quantized value. For a linear codec with n binary digits for sample, the ratio of a full load sine wave power to quantization uh, distortion power S over D is 6n plus 1.8 dBs, where n is the number of bits per PCM word. For example, for a 7-bit word, the quantization distortion would be 6 into 7 plus 1.8, as we put these values in this equation, and we get 43.8 dBs. Adding one bit in a PCM word increases the signal to distortion by 6 dBs for linear quantization. Practical signal to distortion noise ratios range between 33 to 38 dBs, and it depends upon the talker's level. Let's see two different types of PCM line codes. This is the very basic type, which we call the neutral codes. in which 1 is represented with a higher value of voltage and 0 is represented by 0 volts. This is called the neutral format. But we can use a bipolar format also, in which uh, each one, or each, which is also called a mark, is inverted if it continues. Every new coming uh, one is inverted. For example, after one this one comes in, and it gives a positive voltage value. After that, we've got this one, which gives a negative value. This one gives a positive. So every new uh, one has a different polarity. The marks or the binary ones have only a 50% duty cycle. They are there are you can observe this in the previous slide also, that the duty cycle of the ones is half as compared to the zeros. There are several advantages to this mode of transmission also. Number one, there is no DC return required. Thus, the transformer coupling can be used on this line. Power spectrum of the transmitted signal is centered at the frequency equivalent to half the bit rate. Now let's see what's alternate Mach inversion. In bipolar transmissions, zeros are coded as absence of pulses. Ones are alternatively coded as positive and negative pulses. Alternation takes place at every occurrence of one. That's why it is called alternate Mach inversion. What is the drawback in it? When a long string of zeros is transmitted, that is, no transitions, the timing problem may arise because the repeaters and decoders have no way of extracting timing without transitions. As we have already discussed, that the timing is extracted when we go from 0 to 1 or 1 to 0. To cater for this problem, uh, what we do is that we forbid long strings of zeros. Codes have been developed that are bipolar but with n zeros substitution. For example, B6ZS or B8ZS. And what it does, it, for example, this P8ZS, it replaces a string of 8 zeros with a particular signal. Now let's see how does the most famous line code, which is used in PCM, how does it work? And it is called the HDB3, high density bipolar with 3 zeros. So in the previous slide we have seen examples for 6 zeros and 8 zeros, but if we have 3 zeros, then the second and the third zeros are transmitted unchanged. Fourth zero is transmitted as the same polarity as the previous mark. Means 1, which is a violation of the AMI, alternate Mach inversion concept. So we basically do a violation of the alternate Mach inversion concept. First zero may or may not be modified uh, um, to a 1 to ensure that the successive violations are opposite polarity. HDB3 is used with European E-series PCM systems and is similar to, we can also call it B3ZS. bipolar with three zeros after three zeros substitution. Now let's see what's inside a regenerator repeater. We have already stated that a regenerator repeater, what it does is that it regenerates the original signal. First of all, what happens is that it observes the input signal that that comes in onto it, and the first stage is an amplifier and equalizer, in which it amplifies and equalizes and forms of a signal like this. And after that, we have got a timing circuit and the regenerator itself. It generates the signal uh, after making a particular decision based on the value that we have equalized, and after that it is converted into a line code here to put on an output. Pulses passing through a digital transmission system face a lot of attenuation due to frequency characteristics of the line, which cause distortion. Regenerative repeaters regenerates and amplifies such a distorted signal and produces a new replica of the original signal. Noise stops at the repeater, but if there is an error or an error uh, uh, done by the repeater in identifying a particular bit, instead of identifying it a 1 as a 1, it identifies it as a 0. It means that it has committed an error. In this case, the errors would add up. Errors would be cumulative, while the noise would stop at this particular point. So, signal processing, how a signal is processed in regenerative repeaters. First of all, the amplification and equalization is done. First equalizer, what does it do? It is a fixed equalizer that compensates for the attenuation frequency characteristics of the nominal section, which is the standard length of transmission line between repeaters, which is normally 6,000 feet. The second equalizer is variable and compensates for departures from nominal repeater section length and actual length. Then loss variations due to temperature also. Timing of the signal output of repeater. The signal output of the repeater must be accurately timed to maintain accurate pulse width and space between the pulses. Timing is derived from the incoming bit stream. The incoming signal is rectified and clipped, producing square waves, and are applied to the timing extractor, which is a circuit tuned to the timing frequency. The output of the circuit controls a clock pulse generator that produces an output of a narrow pulse of narrow pulses that are alternatively uh, positive and negative at the zero crossings of the square wave input. Regenerative repeaters also cause jitter. They are the major source of timing jitter in the digital transmission system. Jitter is one of the principal impairments in the digital network, giving rise to pulse distortion and inter-symbol interference. Now, what line coding is done in a regenerative repeater? Most regenerative repeaters transmit a bipolar alternate mark inversion waveform. AMI has one of the three possible states in any instant in time: plus, 0, or minus. Threshold circuits are gated to admit the signal at the mid of the pulse interval. For example, if the signal is positive and exceeds a positive threshold, it is recognized as a positive value. If it is negative and exceeds the negative threshold, it is recognized as a negative value. If it has a value between the positive and negative thresholds, it is recognized as a zero or the no pulse value. Now let's see the signal to Gaussian noise ratio for a PCM generated line. Noise does not accumulate in the PCM system, but Gaussian noise or the crosstalk or the impulse noise uh, can affect the error performance or the error rate. Errors are cumulative, as I've already told. A decision in error whether 1 or 0 made anywhere in the digital system is not recoverable. Once an error is done, it cannot be recovered. Thus, such an incorrect decision made by one regenerative repeater adds to the existing error rate of the line. Errors taking place in subsequent repeaters add in cumulative manner, thus deteriorating the received signal. In a purely binary transmission system, if there is a 22 dB signal to noise ratio, the system operates nearly error free. We can see a table which defines this, and it is given in table number, let me check, table number 8.1. You can see this. If we have 22.2 dBs or 22 dBs of signal to noise ratio, we have an error rate or bit error rate of 10 to the power minus 11 to 10 to the power minus 10. But as the signal to noise ratio reduces, the error rate all increases, right? Rather, for example, if we have a signal to noise ratio of 13.5, we will have 1 bit in error in when we are checking 100 bits. 1 out of 100 bits would be in error. Now let's see what are the higher order PCM multiplex systems. Higher order PCM multiplex system is developed from the primary multiplex sources, the DS1, which carries 24 time slots plus 1 S bit, which is for framing, and E1, which carries 32 time slots, out of which 30 are for voice voice channels, and two are remaining. The first one is for framing, and the 16th one is for signaling. At E1 and as E1 and DS1 are incompatible, their higher order multiplexers are also incompatible. Let's see how a DS1 can be multiplexed. Two DS1s can be connected here, can be multiplexed here in this stage. This is a multiplexer M1C. What it does, it takes two different DS1s and multiplexes them to make a 3.152 megabits per second DS1C format. It contains two DS1s. If we combine or multiplex four DS1s, which is done in this multiplexer M12, we get a DS2 signal, which is formed, which has 6.132 megabits per second. Similarly, if we have 28 DS1s and they are input to an M13, what happens is that we get a DS3 signal of 45.736 Mbps. If six such DS3 signals are combined together uh, using a multiplexer M34, we get a DS4 format, which consists of 250 to 274.176 megabits per second. These are the higher levels uh, which are achieved by multiplexing. Lower levels of DS1. Now let's see how is it done. For example, uh, four different DS1s are connected, are basically multiplexed together using an M12, and we get a 6.312 Mbps DS2 signal. It is transported over the transmission media and received uh, at another M12, which demultiplexes it into four separate T1s. And let me remind you that each T1 had 24 different voice channels. Now, North American higher standard multiplex, how is it done? The higher multiplex coding, for example, M34 has input from level 3 uh, and the output is at level 4 or DS4. M12 is the second level North American multiplex and DS2 operating from DS1 inputs, each operating at nominal 1.544. We have already discussed it. Let's move forward. This is the multiplexed DS2 frame. You have already seen that we have how we can create a DS2 frame. Now let's see the European standard. In the European standard, we have got E1 digital hierarchy. E1 has uh, 30 voice channels, and while E1 is the primary multiplex in the European system. E2 contains 120 equivalent voice channels. E3 contains 4 E2s and contains 480 equivalent voice channels. E4 derives from 4 E3s and contains 1920 voice channels. And these basically rates will also be useful when we'll study uh, our optical fiber multiplexers and how and we'll see how SDH and Sonnet take in sub DS3 and sub E3 frames into it directly. That would be quite helpful in that case. PCM is now. Let's see oh, how does long distance PCM transmission act. PCM is transmitted by wire pair, coaxial, optical fiber, and wideband radio media. All media are limited by impairments. Every media has impairments, but they are dependent. Those impairments are dependent on the length and the bit rate. As loss between regenerative repeaters increases, signal to noise ratio deteriorates, thus affecting the bit error rate. Depression limits the circuit length in a particular medium as the rate increases. Main five impairments in PCM transmission are jitter, distortion, thermal noise, crosstalk, and echo. Jitter is the short-term variation of the sampling instant from its intended position in time of phase. And here's a new term which is called wander. Longer term variation of sampling instant is called wander. Jitter can cause displacement of ideal sampling instant, degrading system error performance. Slipping in timing recovery circuits causes degradation in the error performance, system error performance. Distortion of resulting analog signal after it is regenerated at the receiver end of the circuit. Random phase modulation or phase jitter introduced at each repeater accumulates in repeater chain and may lead to crosstalk and distortion in the reconstructed analog signal. Now let's see what is distortion. On coaxial cable and wire pair cable, line characteristics distort and attenuate the digital signal as it traverses the medium. There are three cable characteristics that create this distortion: loss, amplitude distortion, and delay distortion. Regenerative repeaters provide amplification and equalization of the incoming digital signal. Slips are a principal impairment in digital networks. There are also trade-offs between loss and distortion on the one hand and repeater characteristics and repeater section length on the other. Similarly, the thermal noise does not accumulate due to regenerative process. Uh, bit errors can, but bit errors can accumulate, and thermal noise can create errors. Errors can be accumulated. Uh, Repeater sections are often specified with the median bit error rate between 1 into 10 to the power minus 10 to 1 into 10 to the power minus 12 bit error rates. Even 10 raised to the power 2 bit error rate gives a reasonable voice performance, but normally 1 in 10 to the power 3, which means 10 to the power minus 3 BER, it is not tolerable. Beyond this is not tolerable. Next impairment in the PCM transmission is the crosstalk, and then we have got echo, and echo is caused by the impedance discontinuities in the transmission line, including repeaters and transmissions terminations, which include MDFs, codecs,